I hope I'm more or less understandable also through the microphone. Okay, so yeah, also from my side, welcome everybody. It's a great pleasure to give this lecture in person. So I'm Joachim. I'm currently based at CERN and have a dual affiliation with Johannes Gutenberg University in Mainz. And in the two lectures today and the one on Thursday, we are going to discuss some aspects of neutrino theory and phenomenology, broadly speaking. And yeah, so the setup I'm using is I'm going to write on my tablet for most of the lecture, and then towards the end, I will also show you some slides with with pretty pictures, basically. Right, and so the plan for today is we're going to talk about neutrino masses, Dirac neutrinos versus Majorana neutrinos, and so on. The second lecture later today will be about neutrino oscillations. And the third lecture, we're going to continue with neutrino oscillations, but we are also going to talk in particular about some intriguing anomalies that have been observed in neutrino oscillations. So, and for the actual writing, I'm going to sit down, so apologies for that. Right. So the starting point for neutrino theory and phenomenology is, of course, how neutrinos fit into the standard model. So you know that the standard model has this intriguing three-family structure with the 6 quarks, up, down, charm, strange, top, bottom, and the 6 leptons, E, mu, tau, and the corresponding neutrinos. So that alone, I think, is already reason enough to study neutrino mixing, because there is this intriguing structure. We observe these 3 families of elementary particles, and within each family, like the individual particles are very different, but across families, like all the up quarks behave in the same way, all the down quarks behave in the same way, all the charged leptons behave in the same way, and all the neutrinos essentially behave in the same way. So it's a bit reminiscent of the situation that chemistry was in at the end of the 19th century, right? People had uncovered the periodic table of the elements. They saw lots of structures, but they had no idea where those structures were coming from, until eventually we understood that there are atoms, and atoms have electron shells, and so on. And well, the hope is that by understanding better the flavor structure of the standard model, we'll eventually also gain similar insights explaining the structure of elementary particles. Okay, so let's then start in earnest. So as I said, the first lecture is about neutrino masses. And the first subsection is how neutrinos arise in the standard model. Neutrinos in the standard model. So let's start with the Lagrangian of the standard model, or rather the part of the Lagrangian that's relevant to neutrino physics. So there's a big sum that runs over the 3 neutrino flavors, E, mu, and tau. And then I'm going to write down now only the terms that are really relevant to neutrino physics. So there's, of course, the kinetic terms of the neutrinos, which look like a standard kinetic term of a fermion, nu alpha L bar, I d slash, nu alpha L. So the subscript L here indicates that we are talking about left chiral fields, well, because the standard model itself does not contain right chiral fields. Then the neutrino interactions, there is the charge current interaction proportional to the coupling constant G, which is the SU2 coupling constant. There is the W field, and then a charged lepton current, gamma mu, E alpha L. So E alpha L are the charged lepton fields, nu alpha L are the neutrino fields. And there's the Hermitian conjugate, which is the coupling to the W minus. And finally, there is the neutral current interaction that will be, that is of course important, but in this lecture, we are not going to focus on it so much. It's again proportional to the weak coupling constant, but now there's an extra factor of cosine of the Weinberg angle here. That's just a reflection of the fact that the Z is not a pure SU2 gauge boson, but a mixture of the SU2 gauge boson and the U1 gauge boson. Well, and the coupling has again the structure of a typical gauge coupling. There's the gauge boson field, and then there is in this case a neutral neutrino current. So in terms of Feynman diagrams, those two interactions, of course, look like this for the W. Oops. Sorry. Let's undo this. So we have, for instance, here a neutrino converting to a charged lepton and emitting a W. And similarly, the coupling to the Z leaves the neutrino field unchanged. Okay, so far there is no mass term, and that is in fact what happens in the standard model. So when the standard model was developed, there was no evidence of neutrino masses yet, so no neutrino mass term was introduced. But now if we want to introduce a neutrino mass term, then we have several options. So let's go through those, and let's first start with the most straightforward way of introducing a neutrino mass term, a so-called Dirac mass term, which just means a mass term that is similar to the mass terms we know from the other fermions in the standard model. So Dirac masses that basically means explicitly introducing right-handed neutrinos with the same mass as the left-handed neutrinos and coupling them to each other. So that is already, in a sense, physics beyond the standard model, because in the standard model, there are only the left-handed neutrinos. So in the standard model, there's only left-handed neutrinos. And this means if we write the neutrino field in 4-component Sphenor notation, that only the upper 2 components of those spinors have non-zero values. So a neutrino spinor in the standard model, a left-handed neutrino, is 1 minus gamma 5 over 2, so the left-handed projection operator, times a 4-component neutrino field. But what this 1 minus gamma 5 factor does is it sets the lower 2 components to 0. So only the upper 2 components are physical. So we can write this, for instance, as, well, let's call it, for instance, chi1, chi2, 0, 0. So this is what the neutrino field looks like in 4-component Sphenor notation. Now, the main hypothesis when introducing a Dirac mass term is that we make also the lower 2 components physical. So Dirac masses mean make also the lower components physical. Make also lower components physical. So in other words, we complement the nu L fields by a field nu right, which is now 1 plus gamma 5 over 2 times the 4-component field. And that can then be written, let's call it chi3 and chi4, for instance. And this now allows us to write down a term in the Lagrangian that couples the 2 fields. So we can now write a term of the following form: sum over 2 flavor indices, alpha and beta, both of them run again over E, mu, and tau. There is a numerical coefficient, which we call the mass matrix, M alpha beta. And there is nu alpha L bar times nu beta right. So one can check that this is in fact a Lorentz invariant coupling now. And if you've seen the standard model Lagrangian, you're very familiar with those terms because that's how all other fermions in the standard model get their masses after the Higgs has acquired its VAF and has been integrated out. So let me say one more word about this mass matrix here. So this M alpha beta. It's a general complex 3x3 matrix. And because at high energies, the standard model has to respect, the Lagrangian has to respect the standard model symmetries, we can imagine this as being given by a matrix Y alpha beta, so a matrix of Yukawa couplings times the VAF of the Higgs, and then it's really exactly analogous to the other mass terms in the standard model. Okay, now that's an easy thing to do. The problem is that we know that neutrino masses are extremely tiny. So in order to achieve this Yukawa coupling here would need to be much smaller than the Yukawa couplings of all the other particles in the standard model. There's nothing technically wrong with that, but it might seem a bit odd. So it's always nice to have an explanation for why a number is particularly large or particularly small. And that's why the discovery of neutrino masses has immediately led to other hypotheses for neutrino mass terms. But before we come to those, let me make one more point. So I've introduced effectively two additional degrees of freedom now. So without the neutrino mass term, we had only the left-handed neutrinos. With the neutrino mass term, we have left-handed and right-handed neutrinos. And I can give you a little bit of intuition why these new degrees of freedom are now needed. So there is now 4 degrees of freedom per flavor. And the intuition for why that's the case is, imagine you have a neutrino. Draw that a little more straight. So here is a neutrino that's traveling in a certain direction with a momentum p. And now in the standard model, that has to be a left-handed neutrino. So let's assume it's a left-handed neutrino because those are the only ones that couple to the weak interaction. So those are the ones that we make and absorb in weak interactions. So that means its spin is anti-aligned with its momentum. That's supposed to be the direction of the spin. But now, if the neutrino is massive, then we can always apply a Lorentz boost. So we can always go to a reference frame that's moving faster than the neutrino, because the neutrino cannot be moving exactly at the speed of light. So there's always a reference frame that moves faster than the neutrino. That's not possible for massless neutrinos, but for massive neutrinos, that's always possible. So let's apply such a large Lorentz boost. And now after the boost, in that new reference frame, the neutrino will now appear to be moving backwards. But its spin hasn't changed. So spin is unaffected by a Lorentz boost. So the spin vector now still looks like this. So that means we now have a right-handed neutrino. So in other words, because for a massive neutrino, I can always do such a boost, I necessarily need a right-handed degree of freedom in my theory. So let's call this momentum P prime, just for definiteness. And that's the reason, or an intuitive reason for why right-handed neutrinos are essential. Okay, but now I said that this way of introducing neutrino masses is a bit unattractive because there's no explanation for why neutrino masses are so small. So let's go one step further and think about so-called Majorana neutrino masses. Majorana masses. So the basic idea behind the Majorana mass term is, well, we've seen that the mass term necessarily has to couple left-handed and right-handed states. But actually, even in the standard model, there is already a right-handed state, namely the antineutrino, right? The antiparticle of a left-handed neutrino is a right-handed antineutrino. So the question is, can we somehow economize 2 degrees of freedom and identify the right-handed neutrinos with the antiparticles of the left-handed neutrinos? And it turns out that that's in fact possible. So let me write this down. So mass terms couple left-handed and right-handed fields. Couple left-handed and right-handed fields. But the antiparticle of mu L is a right-handed field. So could mu R be identical to the anti-mu L? So in order to answer that question, we need to make things a little more formal. So we need to introduce an operation called charge conjugation. So that's going to be a bit of Dirac matrix algebra now. So this operator, charge conjugation, it does the following. So it's an operator that takes a Sphenor psi and moves it to a Sphenor which we denote by psi c, so the charge conjugate of psi c, and that is defined as minus I times gamma 2 gamma 0 times psi bar transpose. So that looks rather ugly. But it will become clear in a moment why this is the right definition. Let's see, do I need to introduce an extra notation here? So let's first check what this operator does with the chirality of a particle. So chirality is the operator that tells you whether a particle is left-handed or right-handed, and it's just the gamma 5 matrix. Remember, the gamma 5 matrix is the diagonal matrix -1, -1, 1, 1. And so the chirality of a particle is given by gamma 5 times the Sphenor. And we now want to know what the chirality of this charge conjugate Sphenor psi c is. So let's write it out. We multiply the gamma 5 matrix by psi c. We replace psi c by its definition. So we insert here minus I gamma 2 gamma 0 times psi bar transpose. We anti-commute the gamma 5 matrix and the gamma 2 matrix. Remember that gamma 5 anti-commutes with all the other gamma matrices. So the minus I now becomes a plus I, gamma 2, gamma 5, and this psi bar transpose. Remember what that is. So psi bar So remember, psi bar is just psi star times, or let's call it, let's call it psi dagger times gamma 0, and that thing transposed. So we can write this as gamma 0 times psi star. And now there is one gamma 0 here in black and one gamma 0 here in green, but gamma 0 times gamma 0 is the unit matrix. So I can simply drop this gamma 0 and put a psi star here. And now I can again look back at my definition of psi c, and I see that what I have effectively written here now is minus gamma 5 times psi charge conjugate. So what I've shown is that the chirality operator applied to the charge conjugate of psi is minus the chirality operator applied to psi itself and doing the charge conjugation afterwards. So in other words, charge conjugation flips the chirality of the field. So this operation C flips the chirality. And because it hasn't introduced, so we haven't introduced any new degrees of freedom, right? So if psi is a left-handed sphenor, then I only have those 2 degrees of freedom available. And the 2 degrees of freedom are the left-handed particle and the right-handed antiparticle. So if I have flipped the chirality, then well, the only right-handed state I have available is the right-handed antiparticle. So the C operator converts left-handed particles into right-handed antiparticles. So it transforms left-handed particles into their right-handed antiparticles and vice versa. So why have we done this? Because now we have a formal way of defining a right-handed state starting from the left chiral field that we have available in the standard model. And that's what we need for a Majorana neutrino master. So what we do now is we will identify the field that we previously called new right. We are going to identify this with the charge conjugate of the left-handed field. I can also show you what we have done here again in 4-component notation, because somehow when I think about sphenos, I always have this 4-component picture in mind. So it's sometimes instructive to look at it this way. So remember that we wrote our left-handed sphenos as an object that was non-zero in the upper 2 components, but 0 in the lower 2 components. And now the charge conjugate, new left charge conjugate, is then well, minus I times the gamma 2 matrix, which is 0, sigma 2, minus sigma 2, 0, times, well, let's call this chi star. So I'm now combining the 2 upper components into one object called chi, and the lower components, of course, stay 0. So I can do this matrix vector multiplication. I end up with 0 I sigma 2 times chi star. So I have from a sphenor that had 2 non-zero values in the upper 2 components, I've now gotten a sphenor that has 2 non-zero values in the lower 2 components. And that's precisely what a right-handed sphenor is. And combining the 2, we can define what's called a 4-component Majorana sphenor. So that's just new left plus new left charge conjugate. So in other words, this is the sphenor that has chi in the upper 2 components and I sigma 2 chi star in the lower two components. So it is a true 4-component sphenor. It has 4 non-zero indices, but only 2 of them are independent. So that's now Majorana sphenor has 4 non-zero components, but only 2 independent ones, so only 2 degrees of freedom. And it has the property that when you apply the charge conjugation to this 4-component object, then what you get back is just nu itself. So it is a sphenor that is its own conjugate. And that's the formalized way of the statement that when neutrinos are Majorana particles, they are their own antiparticles. That's a statement you often read in the literature. Well, but now let's finally use this to write down a mass term. So we can now write down a new type of mass term, which looks as follows. There's a factor of 1/2, which is necessary for proper normalization. There is a sum over flavors. There is again a mass matrix M alpha beta. There is now, however, instead of a right-handed field, we take the charge conjugate of the left-handed field, so nu L alpha C bar, and then we multiply by the left-handed field. And the Hermitian conjugate is still there. But because in this case, the Hermitian conjugate doesn't add anything new, that's why we need this factor of 1/2. Otherwise, this term would be incorrectly normalized. The normalization would then be too large by a factor of 2. There's again a mass matrix here. However, this is now no longer a general complex 3×3 matrix, but it is a symmetric complex 3×3 matrix. Not Hermitian, but really symmetric. Symmetric complex 3×3 matrix. One can easily see that if there was an asymmetric part to M alpha beta, then this part would cancel between the term that I've written here and its Hermitian conjugate. So that's one way of seeing that this really has to be a symmetric complex 3×3 matrix. Okay, so now we've written down formally a neutrino mass term that saves us 2 degrees of freedom. But of course, we still have some unanswered questions. So in particular, we still haven't answered the question for why those masses are so small. So why is M alpha beta so small? And moreover, remember that all of this has to somehow fit into an SU2 invariant theory. And what I've written down here does not obey SU2 invariance. Because if it did obey SU2 invariance, well, in SU2, whatever happens to the charge to the neutrinos must also happen to the charged leptons. But what I did here with the charge conjugation, I can't do that for the charged leptons because I would violate electric charge, right? So if these were not neutrino fields but charged lepton fields, then, well, the charged lepton field itself would carry charge -1. The charge conjugate of the charged lepton field would carry charge +1, but the bar again makes this a charge -1 object. So this whole operator would not be charge neutral if there was a charged particle here instead of a neutral one. So this is writing down this type of mass term is really only possible for neutral particles, not for charged particles. So it is impossible for the charged leptons, and therefore this operator as it stands cannot obtain SU2 invariance. So we need to ask ourselves how to obtain this from an SU2 invariant UV completion. How to obtain this from SU2 invariant theory. Yeah.
This is only a problem for the Majorana term or for the Dirac term?
The question is whether it's a problem only for the Majorana term or also for the Dirac term. It's not a problem for the Dirac mass term because there isn't this charge conjugation, right? For the Dirac mass term, if I go back up, so, well, a right-handed charged lepton carries charge -1. Left-handed lepton bar corresponds to a charge +1 antiparticle. There's one charge -1 object, one charge +1 object. So the whole term is a charge neutral. It's this extra charge conjugation that messes up charge conservation in this case.
Okay,
it's really only a problem for Majorana mass term.
Yep. Any other questions? Okay.
Okay, well, and perhaps the most elegant answer to both of these questions is the so-called seesaw mechanism. Well, you can argue on how elegant it is, and I don't want to go into this, but it's certainly the most popular answer to those two questions. Seesaw mechanism. So the seesaw mechanism was originally developed to explain why neutrino masses are so small, and along the way, it necessitated the fact that neutrinos are Majorana particles. Of course, we don't know whether that's true, but the seesaw mechanism requires neutrinos to be Majorana. So the first tenet of the seesaw mechanism is actually a step backwards. So remember, we've worked so hard to write down a mass term that saves us 2 degrees of freedom, but the seesaw mechanism introduces those degrees of freedom back. So we augment the standard model with right-handed neutrinos, with 3 right-handed neutrinos. Well, one can get away with only 2, but I'm going to do 3 because it's somewhat easier if the number of left-handed and right-handed neutrinos is the same. So 3 right-handed neutrinos, which we are going to call NR. And being right-handed neutrinos, they are singlets under the standard model gauge group. So they don't carry any of the standard model charges. Singlets under the standard model gauge group. That has the advantage, well, because they are singlets, there's actually nothing that prevents me from introducing those particles in this and adding them to the standard model or to almost any extension of the standard model. Now let's look at what the allowed terms in the Lagrangian are. And for illustration, I'm going to drop the flavor indices now, and I'm going to consider only 1 generation for the moment. We're going to get back to 3 generations later. For illustration, consider only 1 left-handed neutrino and 1 right-handed NR field. And I should call this new left as before. So, well, we already know that if I introduce right-handed neutrinos, I can write down a Dirac mass term. So let's do that. The Dirac mass term, if you remember, has this form, just nu L bar times n right times the Dirac mass. But now that we know about Majorana mass terms, this right-handed neutrino field can have a Majorana mass term in an SU2 invariant way. It's a total SU2 singlet, so there is no symmetry it has to obey. So I can, of course, write down such a term, -1/2 m Majorana times nr charge conjugate bar times nr, and the whole thing Hermitian conjugate. So the idea here is, again, that this MD is obtained from the Higgs mechanism. So generically, if we write this as a Yukawa coupling times the Higgs path, and we don't want the Yukawa coupling to have any special value, so we take that Yukawa coupling to be order 1, say similar to the top quark Yukawa, and then this Dirac mass, the quote natural expectation for that is well, it's order the electroweak scale, order the Higgs mass, order the Higgs mass. Now, one can argue on whether order 1 Yukawa is more natural than an order 10 to the minus 6 Yukawa that we observe for the electron, for instance. But let's assume that this is of order the electroweak scale. This MM, on the other hand, well, that's just a free parameter in the theory. There is nothing to guide us where that is, what its scale is. So it can either be extremely small or it can be extremely large. Now let's assume this is extremely large. The motivation being that, well, maybe this arises at some gut scale level or so. That's very hand-wavy, this argument, but unfortunately, that's what the seesaw mechanism is. So this can be very large. So now we still don't know what the physical neutrino masses here are. So in order to make progress here, let's write this in a slightly different way. So let's introduce a 4-component object defined as nu L in the upper 2 components and NR charge conjugate in the lower 2 components. It's just some notation I'm introducing here. There's no deep physics happening here. It's just because I want to write the above Lagrangian in matrix form. And this now reads minus 1/2 N charge conjugate bar times a matrix M times little n plus Hermitian conjugate. And this matrix now has the structure 0, MD, MD, MM. So just to make this this explicit again, to help you see that this is really identical, if I write out the n field again, I have here nu left charge conjugate bar and right bar times this mass matrix 0 MD MD NR times nu left NR charge conjugate. So now if you multiply this out again, you get back the Lagrangian that you can see at the top of the screen now. The reason I've written it in this matrix form is because now it makes it easier to see what the physical masses are. So in order to obtain the physical masses, we need to diagonalize this mass matrix. So physical particles are particles of a definitive mass. So there's not supposed to be any mass mixing anymore. So if I have an off-diagonal mass matrix, I first need to diagonalize it to obtain the physical states. Now diagonalizing that matrix is an easy exercise. So diagonalize M, and based on the arguments I've given before, we are now going to assume that MD is much less than MM in doing this diagonalization approximately. So remember, we assumed that the Dirac mass MD is of order the electroweak scale, whereas MM is many, many orders of magnitude larger. And in this limit, we obtain the following eigenvalues. There's one eigenvalue of order MM and another eigenvalue of order MD squared over MM. And the eigenvectors are there's an eigenvector that is very similar to what used to be the NR field up to an order MD over MM correction. And there is an eigenvalue that is very similar to what used to be the nu L field up to an order MD over MM correction. And that correction, well, I should also tell you what field this is proportional to. Well, it's always the other field. So mu L plus NR charge conjugate. Yeah.
Down the right, but I'm not very.
Ah, yeah, you're right. Yeah, I see it. Yeah, thanks a lot. You're absolutely right. I put NR here instead of MR. So let's fix that. Yeah, good catch. Thank you. Okay, thank you. And there is one thing I didn't tell you, namely here, when you do the diagonalization, what you do get is you get a minus sign here. Now, what does a minus sign mean here? This is, after all, supposed to be a mass. That's supposed to be a physical mass, which is supposed to be positive. But fortunately, we have some freedom in redefining or rephasing our fields. So I can, for instance, simply absorb a phase factor I, so e to the I times pi over 2, into the definition of my new L prime field, and thereby force the mass eigenvalue to be positive. That's what often happens when you diagonalize a mass matrix. You end up with formally complex or formally negative eigenvalues, but you still have enough rephasing freedom in your fields to absorb those phases. Because remember that when you multiply a field by a constant phase factor, that phase factor never shows up in any physical quantity. So you always have the freedom to do that. So this minus sign can be absorbed into a rephasing of new L prime. Okay, so what have we achieved? First, the eigenvectors haven't changed much. So these NR fields, the physical NR fields, the one with the definite mass, they are almost identical to the NR fields that I introduced initially, but their mass is of order mm, so that it's super heavy. We're never going to see those in any experiment in the foreseeable future. So we can ignore them. The new L fields, on the other hand, the physical new L fields are almost identical to my original new L fields from my standard model Lagrangian. So for all practical purposes, their interactions are identical to the interactions of neutrinos in the standard model, but their mass is md square over mm. And remember, md is much smaller than mm. So this is now a very small number. So in other words, my effective Lagrangian at low energies, where low means anything that is experimentally accessible, the effective low E Lagrangian is now simply minus 1/2 md square over mm times mu L prime charge conjugate bar times mu L prime. So that's exactly a Majorana mass term for neutrinos. It doesn't look SU2 invariant, but we have obtained it from an SU2 invariant theory after integrating out those heavy right-handed neutrino fields. And the actual neutrino mass here, this md square over mm, is conveniently small. So for instance, with md similar 100 GeV, so roughly the electroweak scale, and mm similar to 10 to the 14 GeV, we end up with neutrino masses that are md square over mm of order 0.1 electron volt. So we've solved the two problems that I mentioned. We have started from an SU2 invariant theory. We have written down a neutrino mass term without having to explicitly violate SU2 invariance. And we have explained why neutrino masses are so small without having to introduce any parameters to the theory that feel unnatural to theoretical physicists. So the Dirac mass term is of order the electroweak scale, which people feel is natural. Well, and for MM, there was no natural value, so we assumed it to be very large. Because in particle physics, whenever we don't understand something, we assume it's coming from some higher scale physics. And all we've had to do this is to diagonalize a matrix. Yeah. Yes, please.
So you said that it's basically the low energy for everything that's experimentally observable or accessible. And so we limit us by ourselves. Or is there some for higher energies, some model as well?
So the thing is, remember, I've set my right-handed neutrinos at 10 to the 14 GeV. Those center of mass energies are not achievable in any realistic experiment. Now, of course, I already made this aside remark that why should the Dirac mass be order 100 GeV, so the top quark mass? Why shouldn't it be, for instance, be order 1 MeV, the electron mass? And in fact, that is possible, and people consider such theories. In that case, to get the correct neutrino masses, you also need to make the right-handed neutrinos much lighter, namely you put them at the TeV scale. And this is in fact something that is being looked for routinely at the LHC, TeV scale right-handed neutrinos. And in that case, of course, I can't do this game. I can't play this game of integrating out the right-handed fields, but that's not a big problem. I just keep them in and can still work with the theory. Does that make sense, or is this a bit besides the question?
I think I have to think about it for 2 more minutes. But yeah, I think like the logic was already. Yeah, thanks.
Yeah, and given that the whole seesaw mechanism essentially consists of successfully diagonalizing a 2x2 matrix, you would not believe how people are fighting over who invented it first, right? So I'm not going to go into who invented it first, because I'm only going to offend some senior colleagues. But let's just say it has been invented multiple times by multiple people at about the same time. Yeah, and then there is other colleagues working on more formal theory who claim that all that neutrino physicists are doing is diagonalize 2x2 and 3x3 matrices. And of course, that's a great injustice to neutrino physics, because remember, there are 3 flavors. So what we're actually doing is we spend our days diagonalizing 6x6 matrices. Okay. So let's see, I think I have 10 minutes left. So let's spend those 10 minutes talking about how we look for neutrino masses. So as you may know, we know that neutrinos have mass because we've seen them oscillate, and that only works if they are massive. We're going to see later today why. But we've never really measured their absolute mass scale. So what oscillations tell us is only the differences between squared masses. We don't have a measurement of the absolute mass scale. And I'm going to mention 2 possibilities here to do so. I'm not going to mention the best possibility, in my opinion, which is cosmology, because you're going to have a dedicated lecture by Olga Mena on neutrino cosmology. So I'm going to focus here on laboratory techniques for measuring neutrino masses, which of course have advantages over cosmology, but they also have the great disadvantage that they are not as sensitive, at least not yet. So measuring neutrino masses. The 2 ways I want to mention here is direct kinematic measurements and neutrinoless double beta decay. So kinematic measurements just means, well, if you have a particle and you observe its energy and its momentum, and you measure the energy and momentum with sufficient accuracy, then you have all the information you need to compute the mass. So the way this is done is looking at neutrinos from the beta decay of tritium into helium-3 plus an electron plus an electron antineutrino, the maximum energy that the electron in this process can have is given by the Q value of the decay, which is, so remember the Q value is just the mass of the parent atom minus the mass of the daughter atom. Well, but now there is the neutrino. So the neutrino has to carry away an energy at least equal to its mass. And so the maximum electron energy is given by this Q value minus the neutrino mass. So the experimental task is to measure the electron spectrum, and in particular to determine the endpoint very, very precisely. So measure the electron spectrum and look at the exact location of the endpoint. And that's being done. So the leading experiment at the moment in this field is the Cartridge experiment in Karlsruhe. If I still have time, I can show you some pictures of Cartridge. And in the future, there are ideas to do this even more precisely with a technique called Project 8. I don't know why Project 8. I don't know what projects 1 through 7 were about. But let me first also mention neutrinoless double beta decay. So before we talk about neutrinoless double beta decay, we have to talk about ordinary double beta decay. So the idea behind double beta decay is the following. Let's look at nuclei with the same mass number, but different Z. And let's look at the masses of those nuclei. So a pattern that you often observe, and so we are looking at nuclei with A being a constant, is that nuclei with even Z and even A are more stable than nuclei with odd A and with odd neutron number and odd proton number, because nucleons always like to pair up. So each proton likes to pair up with another proton, each neutron likes to pair up with another neutron. And so if there's an even number, that is possible for all nucleons, but if there's an odd number, there's always one unpaired nucleon, and nucleons don't like that. So what we typically have is, let's see if I can draw this properly. Next one somewhat higher again, and let's draw this one here, and then another one there. So we often observe two sets of nuclei that lie on two different curves here. The upper ones are the odd ones, the lower ones are the even ones. So this is odd, so meaning odd neutron number, odd proton number. And the ones here at the bottom are the even ones. So they have a lower mass, which means higher binding energy. Now, in nuclear beta decay, you move here along the z-axis. So in a nuclear beta decay leaves A constant, but it converts neutrons into protons. Now look, for instance, at this nucleus here. It would like to undergo a beta decay this way here, but it can't, because the nucleus that lies just below it is heavier than itself. But what it can do is it can directly go two steps. So two nucleons can convert simultaneously. So here, single beta decay is forbidden. But here, double beta decay is allowed. So that, of course, doesn't happen for every mass number, but there is a fairly large number of isotopes in the world for which this can happen, that the direct single beta decay is forbidden, And so the dominant or the leading decay mode of such nuclei is a double beta decay. So the Feynman diagram for such a process is, well, just two beta decays happening simultaneously. So there is a down quark being converted to an up quark, emitting a W, which goes to an electron and an electron antineutrino. And then simultaneously a second down quark suffering the same fate, going to an electron and an electron antineutrino. So far, so good. That's just two beta decays happening simultaneously. But now for Majorana neutrinos, remember that in a Feynman diagram, you can always replace an outgoing particle by an incoming antiparticle. So in particular, I can replace, in principle, an outgoing neutrino here, an outgoing antineutrino by an incoming neutrino, and I would still have a valid Feynman diagram. Now, of course, I don't have any incoming neutrinos because I don't have a huge neutrino flux. However, if neutrinos are Majorana particles, then the other outgoing neutrino here, the other outgoing antineutrino is simultaneously a neutrino, because for Majorana particles, particle and antiparticle are the same. And that means I can, in fact, connect the two neutrino lines. So for Majorana neutrinos, I can draw the following diagram. I have two outgoing electrons here, and I have connected the two neutrino lines here. So here I have a neutrino, and because I need to convert a, well, I need to go from antineutrino, from outgoing antineutrino to incoming neutrino, I need one insertion of the neutrino mass. So this little x here means proportionality to the neutrino mass. And that's the crucial point. So this diagram, which, by the way, people call the lobster diagram, and my drawing skills are not sufficient to show you why. This diagram is proportional to the neutrino mass. So by measuring the rate of neutrinos double beta decay, we can, in principle, measure the neutrino mass. So by measuring the neutrinos double beta decay rate, beta decay rate. We can measure Majorana neutrino masses. So two important comments here. Well, first of all, this works only for Majorana neutrinos. If there's Dirac neutrinos, I cannot connect the two neutrino lines, so this diagram won't exist. I will never ever measure this C neutrinos double beta decay. In other words, if I see neutrinos double beta decay, I immediately know that neutrinos are Majorana particles. And the second comment is, well, this diagram is proportional to the neutrino masses, but unfortunately, it's also proportional to a nuclear matrix element. And nuclear matrix elements come with large uncertainties. In this case, the uncertainties, well, they used to be an order of magnitude. Nowadays, they are maybe a factor of 2 or so. But that introduces some uncertainty as well. And it makes it hard to estimate what exactly the sensitivity of any given experiment to the neutrino mass is. And also, if there is an observation at some point, it also means some remaining uncertainty in the value of the neutrino masses. So that's my final comment before the coffee break. Large nuclear matrix element. Uncertainties, let's say, need to be overcome. Well, need to be taken into account. Okay, and I think since my time for today is up, I'm going to stop writing here. Yeah, and we'll continue after the coffee break.
Thank you, Joachim. Are there any questions? Yeah.
For the neutrino masses determination from the beta, so like what Katrin is doing, I never quite understood why the reason is. I thought they could only ever set limits and never like actually define the neutrino mass from that experiment.
But that's just because the sensitivity of their spectrometer is such that they are not expected to go down far enough to see the neutrino masses that we think exist in nature, given the constraints from cosmology. So cosmology tells us that the sum of neutrino masses, the sum of all three neutrino masses has to be less than something like 0.15 electron volt or so, depending on whom you ask, depending on what data sets exactly you include. But Katrin sensitivity is somewhere at the 0.2 eV or 0.3 eV level for a single neutrino mass. And so they are not expected to really measure the physical value of the neutrino mass unless there's something weird going on. So you could imagine extensions of the standard model in which cosmology might be fooled to give you a false limit. You could imagine scenarios with sterile neutrinos in which, so extra neutrino flavors in which Katrin might see something, but I agree, the generic expectation is that Katrin will set a limit.
Okay, so the problem is the sensitivity and not that it's intrinsically impossible. Yeah. Okay,
right.
Thank you.
In principle, the technique could go lower if you were able to build even bigger spectrometers.
Okay, thank you.
Right.
This mass is the effective mass of the electroneutrino, or is a massive eigenstate?
Yes. So what Katrin will be measuring is
effective mass of anti-electroneutrinos.
Yes, effective mass of anti-electroneutrinos. Very good. So I hope I get this right. So the effective mass that they are measuring is, I think, U alpha I squared. Which way does it go? Is there a... Okay, let me not write this down because I will only make mistakes. I will only forget some absolute values, but it is a specific combination of the three neutrino masses. If they had even higher sensitivity, then they would be able to see the three masses individually. Because imagine you have an experiment with extremely good mass resolution, then you'd be able to determine which neutrino mass eigenstate you have emitted in any given event. So what you'd see is that the endpoint of their spectrum, so the way this typically looks is if you have here the energy of the electron and here just the number of events, then, well, in the vicinity of endpoint, for massless neutrinos, this is something that looks just like a straight line. Now, if neutrinos are massive, then that straight line, it turns over a little earlier. So here, the classical endpoint, that's the Q value. So it turns out a little bit earlier. And if you have good enough resolution to resolve the three individual mass eigenstates, then what you would see is, you would see kind of, I'm not sure if this comes out well in the drawing, but you would see three kinks here, one corresponding to each mass eigenstate. So you'd be seeing three superimposed spectra, one for events in which a nu1 is emitted, one for events in which a nu2 is emitted, one for events in which a nu3 is emitted. And those three individual spectra have slightly different endpoints, and you'd be able to discern those.
But this is for Katrin, right?
This is for Katrin, yes, and Project 8 and experiments like this. And by the way, now since I've drawn this, I now also remember exactly how the formula for the effective mass looks like. So what they are measuring is sum over I U alpha I square times MI. So basically for each of these three individual processes, the rate is proportional to modulus U alpha I squared. That's just the coupling constant appearing at the vertex. Yeah.
But for the two-raised double beta, that will not be possible, I think.
No, for neutrinos double beta decay, you always, well, there's always all three mass eigenstates contributing to the amplitude. But since the external particles in your Feynman diagram, in this case, are identical, you cannot distinguish the three processes. You always see the superposition of the three.
So one last question. And then we have
On the mass production mechanisms, I hear that nowadays people are quite keen on trying to explain the smallness through this dimension 5 operator that makes the Higgs field act twice and suppress the coupling.
Sorry?
I hear that people do this thing where they essentially make the Higgs field act twice, and that suppresses the Kawa coupling through this dimension 5 operator.
You mean the Weinberg operator?
Sorry, yeah. How do you feel about that? And can you talk a bit about
Well,
this?
effectively, the seesaw mechanism generates the Weinberg operator.
Right.
So effectively, that's what the seesaw mechanism does. If you integrate out the right-handed neutrinos, then what you get is the Weinberg operator. And then if you remove also if you replace the Higgs field by its VEF, then you get what I have written down.
Okay. Okay.
So that's exactly what the seesaw mechanism does. But it's also what other neutrino mass mechanisms do. But of course, the challenge is you still need to explain the suppression scale of this dimension 5 operator. And that's one of the things that the seesaw mechanism achieves. So it explains the suppression scale well by having a heavy particle at a very high scale. But there's other ways of getting the Weinberg operator. For instance, when you have a triplet Higgs field. Now, triplet Higgs fields have their own problems because they are hard to hide from electric precision tests and so on. But you can do this. You can introduce a Higgs triplet and then remember that in SU2 combinatorics, 2 plus a 3 plus a 2 can give you a 1, a singlet. Mm-hmm. So a coupling of the two charged lepton doublets to a Higgs triplet can give you a singlet operator. And then when this triplet Higgs acquires a VEF in its neutral component, then that's precisely the Weinberg operator again. But then you have to explain why the VEF of the triplet Higgs is so small, and simultaneously its mass has to be large enough, and it has potentially a doubly charged component that is hard to hide from colliders, and so on.
Okay, thank you.
You're welcome.
Okay, let's thank Joachim again.
Yeah.
So we have a coffee break now until 10 past 11, so for half an hour, yeah? Okay.